Welcome back. It's my pleasure to introduce Professor Martin Müller as the first of two keynote speakers today at Advances in Computer Games 2023. I first met Martin Müller in 1994 when he was a PhD student at ETH Zurich, working on his thesis to do with computer games, in particular, Computer Go. Our paths crossed a few years later in Japan when I wanted to recruit him to the University of Alberta. I was to meet him at a train station, and given the throngs of people, I wondered how I could find him. And he just told me very simply, just look for the tallest person. And I scanned out over the hundreds and hundreds of people, and Martin towered over everybody. I used that opportunity to recruit him to the University of Alberta. He came and has been a wonderful experience for our department and for Martin. Today, he's a professor of computing science at the University of Alberta, a Canada AI Research Chair, and the DeepMind Chair in Artificial Intelligence. Martin's main area of research is heuristic search, with its complex interactions between search, knowledge, simulations, and machine learning. Application areas that he's worked on include game tree search, domain-independent planning, combinatorial games, and Boolean satisfiability solving. Martin has worked on Computer Go for 30 years. He's known for the development of the open source program Fuego. In 2009, this program became the first to win a 9x9 Go game on even terms against a top-ranked professional human player. And with his students and colleagues, Martin has developed a series of successful game-playing programs, planning systems, and SAT solvers. And just as a comment, Martin's passion about Go included co-supervising a PhD student, about 15 years ago, named David Silver. Of course, David graduated and went on to be the lead author on the AlphaGo series of programs that eventually realized Martin's dream of creating a world-class computer Go playing program. We are delighted to have Martin be a keynote speaker at this year's ACG. Over to you, Martin.
Thanks a lot, Jonathan, for the kind introduction. I'll try to share my screen. Okay. I assume that's working. So thanks to all the organizers to invite me to talk. It put me on the spot a little bit because we have a number of ongoing projects, but I felt none of them was really ready for prime time. But they all involved solving games. So I talked to Michael, the organizer, about just giving kind of a more survey-like talk on the solution methods for two-player games. And he thought that was a good idea. And then I actually tried to do that, and it grew and grew and grew and grew. So I found out it's an enormous task. So let me share with you what I found, and let me also apologize in advance that I have not covered nearly everything that has been done over the last 20 years in this area. And I also need your help to complete this survey. So let's get started. So in some sense, this talk is supposed to be an update on a 2002 survey by Jaap van den Herik and Jos Outerwijk and Jack van Rijswijk. And I didn't realize at the beginning when I started preparing, but there has been a huge amount of progress all in the last 20 years on the solving games. So I'll do a very brief introduction to the methods because this is a games conference. I think most of you will know most of the basic methods, and I will focus on the games themselves, the games that were solved, how they were solved, which games were solved. And to avoid this becoming just a long shopping list, I try to also group it by methods and intersperse in some places more general discussions of what some of these methods are and how they work in principle. Again, no details in a broad talk like this. And then near the end, I'll talk about some of the current and future challenges in the area and how we can make further progress in the next 20 years. Okay, so let's start with the AI journal paper, Games Solved Now in the Future. That was a broad, exhaustive survey of the field as of that time. And even so, games is a much larger field, so they decided wisely to focus on what we call two-player perfect information zero-sum games. And I think the terminology is clear for everyone. Perfect information means you know exactly the state of the game. There's no hidden secrets that the opponent may be hiding from you. And zero-sum means adversarial games, so instead, as opposed to cooperative games. So whatever I win, the other player loses. Throughout the talk, I'll use the terminology that's used in that paper and also comes from Victor Ellis's seminal thesis. So we'll talk about ultra-weakly solved, weakly solved, and strongly solved as three different categories of how much a game is solved in a certain way. So for ultra-weakly solved, the traditional example is hex. So in hex, there is a what mathematicians call a non-constructive proof that the first player can win on any n by n board. So we know mathematically that on a billion by billion hex board, the first player should win. But the proof is non-constructive in the sense that it works by contradiction. We assume the second player wins, and then that gives the first player also a winning strategy, and it can't happen that both players win, and therefore it has to be a first player win. But of course, we have no idea how to play on a billion by billion hex board. So that was the weakest category of solving. And in this case, the arguments are typically not computational. They are mathematical or based on symmetry or structure. By far, the most common type of solved games that we'll see is what's called weakly solved. I think it's a bit of a strange term because it's still a mathematically complete proof. So what we mean by weak against strong is how many positions in the game we have solved. So weakly solved means for the standard starting position of the game as it's in the rule book, we know how to win, and we also know a strategy how to always win no matter what the opponent does. So if I just write solved, this is the category we talk about. And of course, the third strongest category is strongly solved, where we know everything about the game. So no matter the opponent or the person who's testing our proof can set up an arbitrary position in the game, and we will still be able to figure out the winner and how to win from that arbitrary starting point. Another important classification that's used in this paper, but I decided not to include it here because there's already enough numbers in my talk, is the classification of games in how difficult they are to solve. And that's in terms of state space or game tree complexity. So they have two different measures of complexity. And you can find all these answers, all these numbers in the original literature. I think it's too overwhelming to add all these numbers everywhere, so I skipped that and hope you forgive me. Okay, so what games were solved in the last 20 years? So it's astounding how much progress has been made, and both in terms of general purpose algorithms, but also in terms of digging deep on specific games and doing whatever it takes to solve them. So I'll have many examples in the rest of the talk. I just want to point out these are 4 highlights for me. So there was the solution to Avari in 2002, checkers, of course, in 2007 with Jonathan Schaefer. Michael Bowling's group solved heads-up limit poker in 2015. And a very, very recent result, just a few weeks ago, Takizawa in Japan announced that he solved the game of Othello after decades of work in building strong programs. It has finally been completely solved if the preprint. It looks good. I mean, okay, so these are the highlights, and I'll talk in more detail about all of them and many other games as well. Of course, there's many more games that are too complicated, too hard to solve completely, but even there we have many results either on smaller board sizes or restricted to, let's say, just the end games and so on. And I'll try to cover much of that as well. My review is still mostly focused on the same class of games that were in the survey paper, two-player perfect information zero-sum games. That said, I will do one short detour and talk about imperfect information games such as poker. All right, so that's the plan. Before we do that, just a very brief overview of the basics of solving a game. Most of you will know most of this stuff. It's just so we're all on the same page. So the first question, of course, is what do we mean when we say solving a game? And sometimes the term is used too loosely, but let's stick to the technical meaning. It's what is the result, to find out the result of a game if both players play optimally. Of course, the next question is, what does it mean to play optimally? And what I mean is to follow minimax, right? So the player maximizes their score, the opponent minimizes their score. If we don't have a score, if it's just like win, loss, draw, then we just say a win is the highest score and the loss is the lowest score. And then we can use the same kind of algorithms. We also assume that the games are finite. I didn't put that here. And that we can get exact results in terminal states because the rules of the game will tell us if the game is over, who won. And then, at least in theory, it's simple. It's just a recursive call, right? It's the minimax procedure. If it's our turn, we take the maximum over all our moves. And then it's the opponent's turn, and they take the minimum. And then it's our turn, and so on. So it's a nested, maybe very, very deeply nested minimax function that evaluates all the states we could reach. And if it's nested deeply enough, then we will be evaluating through terminal states and getting exact results. And then this whole expression will be the value of the game. So that's the goal. Figure that out. And of course, what I wrote here is the most naive way of doing it, which in practice is much too slow to do. So what are solution methods in practice? Actually, sometimes that's not too slow. Sometimes you can use large-scale computations. You can use brute force, find all the legal states, find all their minimax value, and you can do that in many cases in a backwards way, start with the simplest positions and then back up wins and losses until you reach the start of the game. So that's retrograde analysis. Or we can do it in a forwards way with forward search, and there's many standard search algorithms like alpha, beta, proof number search, depth first, proof number search, and Monte Carlo tree search variations that allow you to solve the games. The other big component is knowledge-based methods that allow you to figure out exact solutions without search. And that can be based on mathematics, or it can be based on things like symmetry arguments. If you solved one state, and then you can prove that another state will have the same value. All right, and part of the knowledge-based methods are still heuristics, right? So heuristics dominate in the area of playing as opposed to solving games. But the nice thing is that most of these heuristics also help to speed up the search for exact solutions, such as move ordering and alpha beta, right? If we can look at the winning move first, or the strong winning move that leads to a quick win, then if we have knowledge to sort our search, organize our search in that way, it'll be much, much more efficient. All right. So alpha, beta, Boolean minimax search. I don't want to say much about it, right? Everyone knows that's the first thing you learn. It's still a standard approach used in many of these games, as you will see. And over the decades, there's been a huge number of enhancements and heuristics, some general, some game-specific. Just mention the standards like iterative deepening, where you increase your search depths, transposition table, where you can use the fact that the state space is not a tree, but a directed graph, where you can reach the same position in multiple ways. And there has been work from Kishi in our group many years ago on efficient solutions to the problems when that you have when you have different paths leading to something that looks the same but may not be exactly the same because of the history affects the legal moves and the results. Yeah. All right. So those are the basics of alpha beta. They're still fundamental for solving games, not just for playing. Proof number search and depth first version of it is specifically developed to solve games more than play games. They are very powerful, especially when there's narrow and deep lines that can lead to a quick proof, whereas if you do the usual one level at a time search, it would be much slower. So there is no clear winner, right? For some cases, alpha beta is more reasonable. For other cases, you need the depth first behavior or best first behavior that you can get from proof number algorithms. Again, so a bunch of us wrote a survey paper more than 10 years ago, and I think that's still a good one to read about this family of methods. Okay, finally, last but not least, there's a Monte Carlo tree search solver, which is a modification of the heuristic method of Monte Carlo tree search. I mean, we know even regular Monte Carlo tree search in the limit converges to optimal play, but the limit can take a very, very long time to happen. So this is a modification that adds the minimax logic directly into the framework of Monte Carlo tree search. So it will be able to lead to exact proofs in traditional minimax fashion, but embedded in Monte Carlo tree search and using the power of MCTS to find strong lines of play. And yeah, so that'll be one of my future work sections. We have 3 very strong and very different algorithms. How can we even compare them? And as far as I know, there's still no single large-scale evaluation that would shed light on this question. Which of these algorithms should I use if I work on solving a new game, for example? Or should I use all of them, which sometimes we do? Okay. So that's my overview. Let's move into specifics. What are the techniques and how did they solve games over the last 20 years? So the first category is, in some sense, the easiest to understand, which is the large-scale computation. So we basically built a database to strongly solve the game. For all possible states in the game, we compute their minimax value. And very often that's done in a bottom-up way by what the process called retrograde analysis. If you want to know all the states, right, the earlier states depend on the values of the later states. So it makes a lot of sense to start with the simplest cases and back it up. I'll show one example in a little bit more detail. That's the game of Ovari. But I'll mention here another large-scale example that's not so well known. There's the game called Pentago. And I used to have a picture here. I don't know what happened to it. It's a game where you have a board where you can rotate parts of the board, play pieces. It was solved by Irving in a massive computation on a Cray computer almost 10 years ago now. And he claims that at that time, that computation of more than 10 to the 15 states was one of the largest games solved. It still has a very nice online player, so you can actually play through the proof, and it shows you for each move, is it a win, is it a loss, is it a draw, and you can click on it and follow the game. All right, so let's talk about retrograde analysis, just the basics. There's many variations on it, depending on how complicated it is to deal with loops that can affect the algorithm. Okay, we strongly solve a game or a kind of self-contained part of a game, such as endgames with small number of pieces. We built a complete database, all states and their minimax values, and it proceeds backwards from the end of the game. So there's a iteration, right? We have a database with all the known values that we can get from the rules, right? Terminal states of the game. And then we just basically repeatedly go over the database and try to find new states to solve. For example, states where we can win in one move, right? If there is a state where it's our turn and we can play a move to reach a win, a known win, then we can add these values to our database. And if you have all wins in one move, then we can compute all wins in 2 moves and so on. So that's the basic principle of retrograde analysis. And we continue until we make no progress, right? Until we reach a round of computation where there's no new state that leads to a known result, like a win or loss. What do we do with the ones to the left? Well, the game rules have to tell us, and typically those are all draws where no player can force a win. Usually it's declared to be a draw. All right. So let's look at the Avari solution from 2002 by Romain and by Henry Ball. So Avari has almost 1 trillion reachable board positions, and it was solved by retrograde analysis by starting with the simplest positions with 1 stone on the board and 2 and 3 and so on. The search was parallelized to a, at the time, fairly large parallel system, more than 100 processors, large memory, and all connected. And the real technical progress here is in the smart parallel algorithm. So how to make this system work together to solve basically a single large computational problem. I put a picture here to show that it's a difficult game, right? So these are the distribution of scores in the whole database. This is number of positions in billions. And you see most of the positions are fairly close to 0. And yeah, the starting position was a draw, so the score of the starting position is one of these 100 billion positions in the middle on the red part with 48 stones. All right, so this is, I would say, a typical result of strongly solving a game. Okay. So what if you cannot build the complete database? So the next step is to try to combine large-scale computation in the forward and way, but backstopped by databases. So you work on the game from the front and from the end, right? You're doing a search from the start of the game, but to stop the search earlier, you try to build very large endgame databases to cover the last phase of the game and reduce the search depths you need. So you have to search from the start of the game until you hit a known position with a known value in your database. And often this, for the games I'll talk about, this search is so large you can't just do a single search on your laptop. Instead, it's often a massively parallel search process where you have an opening book on a disk and you decide where to expand it in order to complete your proof as efficiently as possible. And so of the 4 games I highlighted, 2 of them are in this category. One is checkers and one is Othello. So let's talk about checkers. Probably I don't need to say too much because it's so well known. It's approved by Jonathan and Neil and Ingvi and others. Checkers was proven to be a draw, and it combined many, many techniques in this way. If you look at the picture, that's the state space of checkers, sorted by number of pieces on the board. So the starting position has 24 pieces. The end of the game, 10 or fewer pieces was covered completely by databases. And then a proof tree was grown in this part of the state space that's actually reachable. So the part of the state space was built out as an opening book, and then the remaining gap between the book and the databases was filled by doing searches to solve more and more positions in the database. So massive endgame databases up to 10 pieces, massive opening book on disk with seeded lines. So these are known strong moves that hopefully speed up the proofs if you just use those moves wherever you can. And then a large-scale parallel independent searches to bridge those gaps to solve a lot of these positions on the fringe of your current proof. One interesting aspect of this work is they use 2 strong solvers with different technology, alpha, beta, and depth-first proof number search, to do these searches. And they both had different strengths and weaknesses, so they combined were effective. And there's a lot more technical things that I didn't cram on the slide. Read the paper. And but these searches were so large that the intermediate search positions in this area were not solved they were solved but not stored in the database, but they can be recomputed on demand. Okay, and so the end effect was there were enough exact values and bounds on values computed that the root, the starting position of checkers, was proven to be a draw. Okay, very recently, Othello got solved. Similar computation, huge scale, so more than 10 to the 18. So that's a billion positions involved in finding the proof. Othello, also a draw, as was suspected. Yeah, so the state space of Othello is quite large. Here I did put some numbers. And to solve the state space, this number of positions was searched. The search was a three-step process. The first one was an opening book. So the starting position is 60 empty squares, right? 4 are filled on the 8x8 board. So the first 10 moves were exhaustively generated. And then there was a guess of a proof tree. So if you can prove just 2,500 of those positions to be draws, then that proves that the whole game is a draw. The second step was expand all these positions with 50 empty and do a big search down to 36 empty. That at that level, it had more than a billion positions. And finally, from 36 empty until the end of the game, an existing strong solver was adapted to solve all those positions that were needed to complete the proof. And it was done on a massive computation hardware. Several supercomputers were involved. So here are the numbers, right? More than a billion subproblems, and each of them was solved on a supercomputer. And the end solver from 36 empty till the end of the game could solve about 10 million positions per gigahertz per core. So it was a very sophisticated software piece that's used at the bottom end. Okay, so that's Othello. So these are two representative games where we combine endgame and also large-scale computation. Okay, to get to our fourth highlight game, let's do a small detour and talk about games with imperfect information. So imperfect information means that, yeah, you don't know the complete state of the game. So like you don't know what cards the opponents are holding or the opponent is holding. So that's private information. Or there could be cards that no player has seen yet. For classical board games, that's the family of dark games, right? So where the opponent, there's a referee and only the referee sees the opponent's move, but you don't see the opponent's move and you have to still decide how to play. Another example is simultaneous moves, where you know the previous state of the board, but you don't know what move the opponent is playing at the same time as you are. These games, there are strong connections to our kind of games. They're covered by the core principle of the Nash equilibrium, which explains optimal play in these games. It's more nicely behaved if there's only two players and it's a zero-sum setting. In that case, the Nash equilibrium has a definite value, and it's kind of like our minimax value. It behaves in the same way. The difference is, of course, it becomes an expected value because you cannot control completely the game because it depends on that hidden information, what actually happens. And it makes games much more complicated, much more difficult to solve. And one of the reasons is that in general, you need a mixed strategy. You cannot just play one move in the same state all the time. And rock, paper, scissors is the well-known example. If you always play rock, you will not win many matches. So you need to mix it up to avoid giving the opponent your hidden information. I'll highlight two examples, poker and the sumo pushing game. So poker, everyone knows poker. It's a whole family of card games, and it is based on bluffing about what hand you're actually holding. And heads up means there's only two players. Limit means that the size of the bet, money that's bet, is controlled. And so there's only a very small number of distinct actions that you can choose at each point in time. You can grow out something like a game tree, and it'll have about 10 to the 14, what they call decision points. It's not quite the same thing as states, because again, to know a state, you would have to know what the opponent holds in their hand, which you don't. There's standard algorithms that have been very successful in these games called counterfactual regret minimization. And to solve this heads-up limit hold'em poker, they invented an improvement on this algorithm and showed that this improvement actually, in practice, converges to the optimum, which is the Nash equilibrium of this game. So if you look at the graph, this is a measure of what the worst possible opponent could beat you by, and it's called the exploitability. And here you see computation time, and you see over time, basically, your algorithm becomes better and better in the sense that even your worst nightmare opponent could only take a very, very tiny amount of money from you if you kept playing your whole lifetime. And that's what they call essentially solved. So a lifetime of play basically is not enough to prove with any confidence that you have been beaten by that all-knowing superhuman opponent. Okay, this was a large computation, so here's some numbers. 200 nodes, 24 cores each, memory. They split the game into a massive number of sub-games, and they ran over 1,500 iterations of these CFR algorithms, and that's what you see in this graph, is how the strategy improved over those 1,500 iterations. All right, yeah, and it took a lot of computation and memory. Okay, so the end result of this computation is basically a very large table that tells us, that tells you the probability with which you should choose each action in each of these decision points. And that allows you to play poker on a level that's indistinguishable from perfection. All right. So that was a breakthrough result, both in terms of new algorithms and also in terms of what types of games we can actually solve. Okay, I want to mention one other imperfect information game because it really illustrates the special difficulties of these games, even though the game itself is very simple. So Oshizumo, it's inspired by the Japanese sumo wrestling. There's two players, each of them has 50 units of energy. They start in the middle of the board. It's simultaneous moves. In each round, you select how much energy you want to expend right now for pushing the opponent. And for example, if I spend 4 units of energy and the opponent only spends 2, that means I win this round, so I get to move. So the dot represents the pair of wrestlers, so I push forward. And if I manage to push the opponent off the board, I win. And if both run out of energy, then whoever pushed it over more to their side wins. And if they're still in the middle, back to the middle, then it's a draw. So it's a simultaneous move game. There's a minimum bid, could be 0 or 1. And yeah, to make a long story short, Michael Burrow solved this game, and he found that there's very, very complex mixed strategies that are required to play this game well. And here's an example in the starting position where both players have 50 energy and you're in the middle, so position 0. He found the value, right? Let's call it the minimax value of 0. So it's a fair game, which it is by symmetry. But here are the probability distributions over how much energy you should put into your very first move. So it's a huge mixed strategy. You can bid anything from 0 to 10 with some probability. And yeah, here's the same calculation if the minimum bid is 1. So you cannot bid 0 anymore. So this is really, for me, this was a very surprising example that you can solve these kind of complex imperfect information games with algorithms. Okay, let me move on back from impartial games to our type of games. Of course, Game of Go is still my favorite. And the last results, there were 2 results in the 2000s posted to Eric van der Werf and his supervisors, Go, even on small boards, is very difficult and challenging. Here's examples of optimal solution on a 4x7 board, and it's very deep and intricate. It used a lot of game-specific knowledge to stop the search earlier. I'll come back to that point a little bit later when I talk about these methods. The work found a number of mistakes in human analysis. So again, proving the power of complete search and actually solving games. On difficulty in Go, you can have more moves than the number of points, right? This is a 28-point position, and the main line is more than 30 moves deep. Also, the rule variance can make the game easier or harder. Here's a table of boards that have been solved, at least one rule set of the game of Go, and you see boards up to 4x7 and 5x6 have been solved. And I'll talk in the end about 6x6 because that's one of the projects we're working on. All right. The game of hex, another classic board game, connection game, right? So you try to connect two sides, your own two sides, with a string of stones. That's the traditional prime example of the ultra-weakly solved game, right? There's been a proof in the 1950s that's the first player win, but it does not give us any hints about how to actually play. 6x6 has been strongly solved, so Jack von Rijswijk solved all 6x6 hex positions. And then, sorry, this title refers to the other ones. 7x7, there was Yin Yang, who came up with human-defined strategies to prove starting positions on the 7x7 and later on the 8x8 and 9x9 boards. But Ryan Hayward and his group eventually solved all 7x7, 8x8, and 9x9 positions. So the picture here shows the winning and losing moves on 9x9 board. And last but certainly not least, the 10x10 is known. We have to ask Ryan for the details, at least for the center move on 10x10. All right. So let's talk about knowledge for a minute. So what is game-specific knowledge? What are games where game-specific knowledge was super important rather than more general heuristics or general algorithms? So one game I want to mention is called Domineering. It's a very simple game. You place dominoes on a grid, and one player plays horizontally and the other player plays vertically. So very simple rules, but this is a game where the knowledge-specific rules, game-specific rules to estimate early who's winning or losing had a very strong influence. And that's the only reason that we can solve boards up to 11x11 as done by Jos Atterwijk a few years ago. So these would be completely infeasible searches without that very strong knowledge that can guide your search and tell you very early on who's actually winning. Similarly, I didn't even put in a Go picture. That's sad. There is work for solving the game of Go. It relies crucially on finding wins and losses early by finding what's called safe stones and territories. So those allow you to say earlier on, before the game is over, that one player has enough points that they're guaranteed to win in the end. And there's a pretty large body of work on this. The most recent one is by my PhD student, Owen Randall, last year at CG. And here's an example of the kind of improvements you get from different methods. These are 6x6 positions, which is the next target for solving. This is the move number, like how early or late in the game it is. And this is the fraction of how many of those positions can be solved. These are the static methods, and you see the newest static method is better than the earlier ones. But more importantly, these graphs show if you do a search using this method to decide when a game is won, you can solve more positions earlier in the game in the same time unit. All right. So this is not a branch of. So combinatorial games are just a special type of two-player perfect information zero-sum games, but they have extra structure that allow you to do some things much more efficiently than if you don't have this extra structure. So the key idea is to break a game into what's called a sum of independent subgame, right? If you have the game of NIM, then if you make a move in one of these heaps, you take away some pebbles, it doesn't affect the other heaps. So in that sense, they are independent. Making a move in one subgame leaves the other games the same. So if we have a game with this kind of structure, we can use it to speed up our search. I want to show one example that I'm proud of, which is a solution to Amazon's that I did with Jiaxing Song a few years ago. So we solved the game of Amazons. If you don't know the game, you have pieces that move like chess queens, but they also shoot an arrow, and then that square becomes burnt off and no longer usable. The standard game is much too large to solve. It's 10 by 10 board and 4 Amazons each. So, but we found some results on smaller boards. This is the largest we've solved. It's 5 by 6, so 5 wide, 6 high. And for this board, it's a large search, but there's still kind of relatively simple blocking strategy. So white can block black from enough squares that white can make more moves. We also found, surprisingly, one case that was a second player win. So if the board is very wide and not high, then it seems there's no advantage in going first. There's actually a disadvantage. What's the approach? We built massive databases, but a different kind. So those databases would have local information about subgames of the board, about parts of the board that are disconnected by these blocked off squares from the rest of the board. We computed concepts from combinatorial games called means and temperatures, and we integrated all that into a full board alpha beta search algorithm that could determine early wins and losses by using these concepts. The most surprising thing for me in this work is that it worked even though the number of games, subgames, is relatively very small. It's still much more efficient to do it this way than without these ideas. So if you look at this graph, this is the number of moves from the start of the game, and this is the number of subgames on average during the solving process. So for the first 10 moves, the whole board is one big mess. There's no splitting at all. But then just around 10 moves, you start getting subgames, and you can start using those techniques to help the solver. And on average, in the best case, after about 17 moves, we have a bit more, like 2.2 subgames on average. But even that small number of subgames is enough. So I think this is a very exciting and strong result for combinatorial game theory. All right. The other algorithm I'm really excited about in combinatorial games is the work called Numbers Are Inevitable by Lemoine and Viennot, and that appeared in theoretical computer science. So impartial games are games where both players have the same move, right? If there's a NIM game, it doesn't matter if it's your turn or the opponent's turns, you can pick some pebbles from a heap. And it's been long known that each impartial game is equivalent to some NIM value or some NIM heap. So if I make up any impartial finite game, from theory we know it has the same value as some NIM heap, we just don't know which one. And that can be a very large search process to figure it out. It's like regular minimax search. We know each game will have some minimax value, but we need to do a big search to figure out which one. So what they came up with is a specialized algorithm, a very efficient way to compute these NIM values for impartial games. And then if you have a large game that's a sum of many subgames, if you know the NIM value of each subgame, then you can use the mathematics to immediately get the complete value of the game without any further search. So this work was really a big breakthrough, and I'll show you soon how that showed in the results. There's a more recent work that claims some improvement on this work, but they don't have large-scale evaluations, so it's a bit hard to evaluate. Okay, so here's the game called Sprouts. There's dots, you connect them with a line, you add a new dot. The lines cannot cross. You try to make the last move. Before this paper, this was solved up to 11 dots. They solved everything up to 44 dots. And it behaves like every other game, right? The complexity increases exponentially. So this is a huge breakthrough to solve suddenly games that are 4 times larger than was possible before. It was also applied to an impartial version of domineering. So it's like domineering, but you can play either horizontal or vertical. You're free to choose both types of moves. And before their work, the largest board was 3 by 9, and they pushed it all the way to 3 by 18 and solved some larger rectangular boards as well. And they computed exact name values. So in some sense, that is the most detailed information you can compute. Later on, Jos Autowijk extended these results, and he found some win-loss results for larger cram boards as well. So that's a recent paper. I should make some progress. Dots and boxes were solved by Barker and Korf up to 4 by 5. It's again, that has many connections to combinatorial games, but it's not straightforward. So their approach was alpha-beta search, highly optimized with game-specific improvements. And they found that 4 by 5 is a tie in terms that both players get the same number of boxes with optimal play. Okay, no-go you're going to hear about in the next talk, so I'll skip it here. Fanorona is a traditional game from Madagascar, was proven a draw by Shad, and the pattern is familiar, right? Large endgame database, and then they used the variant of proof number search, PN2, to solve the game from the beginning. Okay, these are some important games. I don't have enough information, so if you have more information on draughts or Chinese chess or backgammon about the techniques and how far they are solved, please let me know. Let's wrap up, talk about towards the future. So what about deep learning, right? Everyone's talking about deep learning in AlphaGo and AlphaZero. There's many algorithms for more complex games that have been very successful. Can we use it for solving? Well, yes, but it's complicated, right? Networks are slow compared to just regular simple evaluations. And in players, that doesn't work that much because we can be selective for both players. In a solver, for the losing side, we have to look at all their moves, no matter how ridiculously bad they are. So it doesn't scale nearly as well. One successful example is the proof cost network by a group in Taiwan, Tirong Wu and many others. In this case, the neural network is trained not to have a value function or a policy, but to estimate the size of the proof. And then you can use this to control, for example, proof number search to go for the cheapest estimated proof. So use it as a strong heuristic to initialize your proof numbers. And for many years, that the group of has worked on kill all Go, where it's a special case of Go where you try to prevent the opponent from making any living group. This is the most recent work along that line, game solving with online fine-tuning in Europe this year. And here's some example of kill all openings that have been solved. So 7 by 7 board, black gets 2 moves in a row and then has to prevent white from getting any living group. So this may be the next game that gets solved. It looks like they're getting close. All right. I also want to mention Tristan's paper on Monte Carlo Game Solver from 2020. And it's an interesting combination where Monte Carlo, the main engine is still a traditional solver like alpha beta, but it uses Monte Carlo tree search and it uses machine learning of playout policies to make really, really strong move ordering for the main solver. And this system works really well. So strong results. I didn't give the details here, but do read that paper. It's maybe not so well known, but it's very good. Okay, let's come to challenges to wrap up. Near term, so those are things I believe should happen in the next few years. 6 by 6, we're working on it. It's hard, it's big, but we're making some progress. There's been a lot of scattered work on combinatorial games. I think there's space for a unified framework of search-based solving of those games, taking advantage of structure. We talked about MCTS solver. How about an AlphaZero based MCTS solver? So take an AlphaZero implementation, but add the capability of backing up proven wins and losses. I think that should be a very nice project. solve more Amazon's positions, read our paper. We know how to do it. We just haven't done it. It's big, but not huge. Like I mentioned before, I think someone should compare all the standard algorithms in a systematic way. Longer term, incomplete information games, they're difficult. There's many mathematical-based approaches. I think there's still space for more search-based algorithms there, but it's a very difficult area. Yeah, other than comparing the algorithms, the standard algorithms, I think there are directions to combine the benefits of some of them, like proof number search and Monte Carlo tree search. And yeah, one of my students is working on that as well. Can we get better handle on proof cost estimates, more deep learning methods to improve those systems? This is much more out in the blue. Can we automatically discover game-specific techniques, knowledge for solving proofs, static evaluation? Think of doing like the static safety solver in Go, but not by humans, but by a machine. Cheap against expensive knowledge. In chess, we have this very interesting situation where we have a very deep, expensive neural network and a very shallow and relatively cheap one, and they have similar performance. So when are these deep but expensive nets useful? Can we compile them into cheaper knowledge? And of course, the big question, which I will not try to answer, is which games will be solved next? Over time, so I'll try to wrap up. Let's look a little bit beyond games. So there's a lot of work, a lot of interest in exact solutions beyond heuristics. And in the end, most deep networks are just that, very, very good heuristics. So one specific example I want to mention is chemical synthesis. It's been formulated as an and/or search problem. So there's a number of successful applications using game tree search methods like DFPN and Monte Carlo on those problems. And one of the pioneers, Abraham Heifetz, has a startup company with a lot of capital. So these ideas are actually used in industry. All right, let's sum up. I hope I've given you a whirlwind tour of the huge amounts of progress that has been made in the last 20 years. And it comes from all fronts. It's not just better hardware, right? I've shown you progress through stronger search algorithms, fine-tuning variants of search algorithms, but also a lot of specialized work on specific games, on specific challenging problems. And we see the impact of, that should be deep learning is just starting to be felt. So that's one area to watch. And let's have another exciting, at least 20 years ahead of solving games. Thank you.
Thank you, Martin, for a wonderful talk. We now have time for a few questions, either through the chat or through the question and answer interface. So please prepare your questions and type them in, and we'll get Martin to answer them.
Would we also speak, or is that impossible?
I'm sorry, Jaap, what was the question?
Yes, I have many questions, but first I have a compliment. So let me start with a compliment. And I would say this was a fantastic talk, really very much covering all kinds of topics. And it implies also that, thank you for giving me the floor, that I could fill in this quarter of an hour with 5 or 6 questions. I will not do so. I will say make one question and let me say one brief question and one, I would say, characteristic question. So to be as brief as possible. My first question is, of course, you did not talk in the end. I would say, when do we solve chess? Is it out of your range, or have you any idea about that?
Okay, first of all, I saw they had a slide on chess and games. I don't know what happened to that slide. I don't.
Well, chess in itself, my compliments, is a 32-piece endgame.
Yes. So I think on the slide that somehow didn't make it into the final talk, I reviewed what's happening in chess endgames, right, from 6 to 7 pieces right now. People seem to be working on 8 pieces, and they seem to be confident that in a few years they can complete 8-piece databases. But yeah, I don't think there will be 32-piece databases. It's out of the question for me. So I don't think chess will be solved in my lifetime. I think that's a fair bet. I'm willing to bet a fair amount of money on that.
Okay, now I'm your I would say companion in that case, because my estimation is that chess will be solved by January 1, 2035.
Okay, so we should
That
maybe
is, but
have a
that was
bet
not
about
my.
that.
Let me give one open question to you. Yes. And that is really what triggers me and you also, because you have some games and they are, let me divide it not in black and white, but let's say first mover and second mover. So most of the games are win by first movers, yes? But
Yes.
there are a few games that are win by the second mover. And you mentioned one of them. But let me give you very brief. So once Victor Alles came to me, and he said that he would like to solve the game of Connect 4. You did not mention that, but it was one of the first one. Oh,
Yes.
sorry. Yeah, that's my wife. Excuse me. I put on. Yeah. Hector said, yeah, I believe that Connect 4 is a win for black, for the second player. And then I said, why do you think so? Yes. And he said, this is an exception because this is zoekzwang. And of course, that is the main this distinction between all the games. The game is for the first player, the win for the first player, they are, I would say, initiatives. They have the initiative, and that's the better one, yes? And some exceptions, and also you have that in chess, that you have zoekzwang and that you can win a game. And so Victor thought that the Connect 4 was a zoekzwang game. In the end, it turned out, and he proved it himself, that it was not true. But now I saw one game that was the game with the dominoes with the 6-4, yes, and that was a win for the second player, yes. If you characterize that now in win for the second player and win for the first player, what is the percentage that you have second players win?
I would be skeptical about percentages because this space is not clear, right? If you talk about percentage, you would have to say this is the space of all games, and then we count the wins and the losses, and then we can talk about percentages. But the space of games is very open and infinite, so I would be very reluctant. But for example, in these impartial games that I talked about, there's a very clear notion using the numbers, right? If the number value is 0, then it's a loss for the first player. And if it's anything else except 0, then it's a win for the first player. So in these specialized situations, we can start to make an argument, maybe how likely is it to come up with a number of 0, right? And one thing that is true in those games, you can always add another small game to make the game a second player win. For example, if you set up some very large sprouts position and it turns out to be a star 5, then you just add a little nim heap with 5 pebbles, and then it's a second player win. So yes. That, in that sense, you could make it 50-50 if you so choose.
Yes, you can construct the games, you would say.
That's right.
Yes, that's
true. For traditional games that are not impartial, it'll be much harder. But
I will stop with questioning because otherwise other people have no questions. But sometimes in personal conversations, we can continue our discussions.
Okay.
Thank you. You did very well.
So, Martin, a question in the chat. When will quantum computers start solving interesting games?
Yes.
Right. I know very little about quantum computers. What I do know is that they use that concept of superposition to basically do many things in parallel. So I think if someone figures out how to use quantum computers to do basically a large-scale parallel search using the quantum effects, then at that point, they will start solving interesting games. But I don't know if that is technically possible or not. I have no opinion on that, and not enough knowledge to answer that.
Okay. You mentioned using opening books during the solving process, but where does the opening book come from if the game is not yet solved?
Right. That's a very good question. Typically, before we start solving a game, we already have very strong computer programs that play the game very well. So the standard approach would be to use a playing program to spec out the most likely lines by trusting the playing program's evaluation. So if you, for example, just assume that the playing program's evaluation is correct or mostly correct, then you can say, okay, if that would be the truth, then which would be the lines that make the game easiest to prove? So that's the usual process. You build a book using the strongest heuristics that you know about, the strongest programs you have. And then, yeah, like in checkers, you just increase and increase and increase the book until you have a proof.
Thank you. Are there any opportunities for solving multiplayer games?
It says Murray Campbell to everyone. So I don't know. For me, as soon as you have 3 or more players, the level of even what is the right question to ask becomes an issue, right? Because you get into coalitions and things like that. So yeah, there is one opportunity for solving multiplayer games, which is to look at 2 teams playing against each other. That's close enough to the traditional 2-player setting. But of course, that's probably not the answer you want to hear. I don't know anything beyond that. What I've read is more complex.
Okay, David Fotland's raised his hand, and I've asked him, I've permitted him to talk. David, did you want to ask your question verbally?
I think it was an accident. I didn't really intend to raise my hand.
Oh, okay. Well,
Hi, David.
There's a question, let's see, in the Q&A about the second to last slide. Can you give us more details on how game tree search methods are applied to synthesize chemicals?
Right, I gave some references there. So the key is in how the problem is formulated as an AND or tree search problem. Right? Traditionally, a lot of search is single agent search, and then for us, that's what we call an OR tree, right? Where we choose this action or this action or this action. When you have an AND or tree, then at some points in the problem decomposition, you say, okay, to solve this problem, I have to solve all these other problems. And so the technical details, it's probably better to read the papers than to ask me. But the basic idea is, if there's a problem that's an AND or tree problem, then you can use the whole machinery of 2-player games, because every game can be viewed, the process of solving these games can be viewed as solving an AND or tree, where the OR node corresponds to when it's our turn and we can pick any one move. We just have to find one move that works. But the AND node corresponds to when it's the opponent's turn, and we need to solve all those options. No matter which branch the opponent picks, we have to win against all of them. So that's the AND node. So any problem outside of games that can be mapped as an AND or problem, we can use a lot of the machinery of game tree search to solve them.
Okay, I guess we're at time, but there is one more question in the chat, so let's just finish it. Dave Gombach asks, can we also consider multiplayer cooperative games?
Right. So I guess if everyone just cooperates, then the minimax theory does not apply. If some players cooperate, then you have this coalition setting that I talked about a minute before, right? So if you have one group that cooperates against another group, then you can map the top level decision-making to a minimax problem. But the question how they cooperate amongst each other, it's basically just an optimization problem as far as I understand. So there's no adversarial component in that part. So of course we can consider those games, but the solution methods may be completely different. I guess that's my general answer.
Okay, we're out of time. It's the end of the session. Perhaps Martin, there is one more question in the Q&A. Perhaps you could just answer that textually, but we are 5 minutes past the end of the session, so I do want to stop it and thank you for an outstanding talk. Obviously, it generated lots of interest. And for attendees, we're taking a short break, and then the next session is coincidentally, or not so coincidentally, session with 2 paper presentations on solving games. So we'll learn some more about the progress of game solving. That will then be followed by our second keynote today from Frank Lantz. So short break, everybody, and we'll see you back in 15 minutes. Thank you.